Hello, my name is Kai. I'm a student at Bunker Hill Community College, and I was part of the Birch Lab this summer investigating a Weyl semi-metal called tantalum arsenide. And notice I said Weyl with an L and not the word wild. That's when people get that confused before. So, a brief outline. I'm going to touch on our group's research questions and areas of interest, as well as the implications of our research. Obviously, I'll talk about the Weyl semi-metal tantalum arsenide, and some of our research methods and the results we've gotten thus far. So, research questions. So our lab is interested in finding and optimizing materials that are sensitive to the mid-infrared range of light, and we hope to exploit the novel physical effects that these materials possess, which have possibilities being applied to better sensing and communications technologies. In particular, the fast current response that you see in a Weyl semi-metal like tantalum arsenide is particularly of interest to us. And in this summer, we've been looking at what happens when you expose a material like tantalum arsenide to chiral or circularly polarized light. So that word, chiral. Something that is chiral is non-superposable on its mirror image. So if you were to put your hands up in front of you and stack your hands like this, they don't match up. That's an example of chirality. So some chiral molecules, for example, include DNA and caffeine, which you're all probably familiar with in one way or another. And particles can also have a definite right or left chirality. So these guys are little cartoons of the chiral electrons that are present in the semi-metal tantalum arsenide. And finally, light itself can also be chiral or circularly polarized. I use the terms interchangeably. So here's a quick example showing the difference between circularly polarized and linearly polarized light. The primary difference is that with circularly polarized light, the electric field rotates with time, so it's essentially like a corkscrew moving in space, whereas with linearly polarized light, the electric field is trapped in a plane and just oscillates back and forth at some fixed angle. So we want to know, and I promise this is the only math equation in the entire talk, whether at room temperature, circularly polarized light can be coupled to these chiral electrons and produce a novel physical effect known as the anomalous Hall effect. So to explain that effect to you, I first have to go over the ordinary Hall effect. So some of you might remember this from your intro E&M class. If you have some conductor, let's just say silver, and you apply a current to it, the charge carriers begin moving through the conductor. If you then apply a perpendicular magnetic field, so perpendicular is 90 degrees to it, the charge carriers get deflected to one side of the conductor. And what happens is you get a charge buildup on one side, and when you separate charges, you get a voltage. And you can then measure that Hall voltage in the transverse direction, which is indicated by the yellow arrow up there. So that's the ordinary Hall effect. So similarly, the anomalous Hall effect is a separation of charge, but via a different mechanism. So if you take a Weyl semi-metal, like say tantalum arsenide, and you apply a current to it, same thing, charge carriers start moving. But if you apply chiral light instead of a perpendicular magnetic field, the chiral light should couple to the chiral electrons in the material and generate a chiral current. So the result is you get a net voltage in the conductor. Likewise, this is right circular. If you use left circularly polarized light, you would have the current flowing the other direction. And the current response is very fast. It's much faster than a current response you might see in a traditional conductor. And we want to know whether this effect is achievable in this material at room temperature. And additionally, just as a side note, we expect that if you apply linearly polarized light, that you would get nothing, because linearly polarized light cannot couple to chiral electrons. So again, the implications of this are that the fast current response in the material might make it useful in fast response thermal, chemical, or biological sensors. So the Weyl semi-metal, which I've said 20 times now, we're investigating, is called tantalum arsenide, and that image you see up there is one of our samples. And what's interesting about this is, again, what classifies a Weyl semi-metal as a Weyl semi-metal is these low energy excitations that are chiral fermions. And the reason I bring that up is because these things are not present in the conductors that you're used to, like in everyday life, like the kinds of conductors that are in your cell phone, for example. which is why this is an interesting material. So that is our sample mounted to a circuit board that we use to take our measurements. So to give you a sense of scale, this block, this is an SEM image. This is approximately 2 millimeters square, and this pink scale bar for reference is 1 millimeter across. And if we zoom in a little bit more, you can see this surface bubble of epoxy holding the sample in place, and this bar is approximately 200 microns across. So another zoom, and you can start to make out the features of the device, and the scale bar is now approximately 20 microns across. So this is very, very small. And with the last zoom, we're actually down to the actual device, and which you can see in purple there. So this is a false color image. This color has been added to it. And this is what we want to illuminate with our chiral light. So part of the reason that the device is so small, you might wonder, like, why can't you do this with a bulk device? It's much bigger that you can see by eye, is that the light will only penetrate but so far into the surface. So by making it as small as possible, you sort of maximize the amount of light actually getting into the device. So the question is, using this, how do you actually measure something like the anomalous Hall effect? And that would just come down to our methods and our equipment. So the first part is the laser table, which is my personal favorite. I think it's the coolest. The setup consists of laser table, pictured there on the left, and our sample stage over here on the right. So I'll go through these individually. So on our laser table, highlighted in red, is the CO2 laser, and the beam path is also indicated by the solid red line. The beam chopper is shown in green. The beam chopper rotates at a specific frequency and is used to chop up the beam pulse. It's a little light segments, if you will. Next is the beam splitter and the MCT, so highlighted in orange and blue respectively. So keep in mind, we're trying to hit a microscopic device using an invisible laser. Okay, mid-infrared light is invisible to the naked eye. So the beam splitter and the MCT work together to help us locate the sample via its reflected light. So the reflected light is indicated by that dotted red line there. Okay. And finally, the last piece of equipment there is called a quarter wave plate in purple. The quarter wave plate takes the linearly polarized light that I mentioned earlier that comes out of the laser and converts it into circularly polarized light. So at that point, sorry, this is just a table from another angle, so you can see the beam splitter a little bit more clearly there. Okay, so at this point, we have our sample mounted to its sample block in yellow. So that's the circuit board that we connect to the computer to take all of our voltage readings. And just to give you a reminder of what you're looking at, that little square in the middle, this is the guy that's mounted to the middle of that circuit board. So that's attached to our sample stage. So you still have the CO2 beam path in red there. And the beam hits a focal lens, which focuses the beam down onto the sample. In pink, you've got the 3 piezo motors. So there's 1 motor per axis, if you think about a normal, like, orthogonal basis. Each motor is responsible for moving the stage in one direction or another. So we can put the laser on different spots on the sample. And then, of course, the tantalum arsenide sample is still highlighted in yellow. And the entire enclosure, in case you're wondering, that is a Faraday cage to keep out any electromagnetic interference. So all of our data gets fed into a computer, and that data sometimes needs a little bit of cleaning, if you will. So as part of my project, I had developed some computer code that would, it's called auto-phasing. It would auto-phase our data set. And all that really means is that the computer would take in the out-of-phase data, in this case some photocurrent response, or photothermal current response, and represent it just in terms of the X component of the voltage, so you see how the image becomes a lot clearer up there. And I did this in LabVIEW, which is the software that does the bulk of the automation of that setup I just showed you. It controls the piezo motors, for example. And the first data set I actually managed to generate looked like this. Beautiful, right? But with a little bit of tinkering, I managed to make it come out like this. So it's a small victory this summer. And speaking of small, taking data with such a small device can be really difficult because the device is so sensitive. You actually don't want the device to blow up. Like these two. So these two devices have the damage circled in red. On the left there you can see a diagonal break in it, and on the right you can see a square break in the middle. Both of these devices detonated because of a sudden spike in voltage. So we wanted to make sure that doesn't happen again because it takes about 3 months to make one of these guys. So in order to prevent that, I also built a breakout box, which is a box, to which the samples are wired for experimentation. And what these allow us to do, we can wire up 2 samples simultaneously. Like I've said over and over, this is a very delicate device, so you want to avoid swapping connectors and touching it as much as possible. So if we can wire up 2 at once, it's a little more efficient. And also, they serve to just keep everything grounded. Here's the box with the lid off. I made the one on the right, so all the connections have to be carefully soldered and checked repeatedly for shorts and things like that. All in all, what this does is it ensures that any sort of buildup of charge anywhere in a system gets directed to the building ground instead of into the sample. So that more or less wraps up the methods, and it brings me to our results. So you probably want to know whether our data shows the presence of the anomalous Hall effect, and the answer is no, not yet. More testing is necessary in that area. But while we were testing an upgrade to our setup last week, we did get some encouraging and rather unexpected results. So we performed a 360-degree rotation scan of our quarter wave plate. And just as a quick reminder, the quarter wave plate turns the linearly polarized light into circularly polarized light. So while we're doing the scan, we didn't expect to see a significant response, because if you'll recall when I talked about the anomalous Hall effect, I said there was an applied current to the conductor. In this scan that we did, there was no applied current. We were just hitting it with the light and looking at what happened. And we got this. So this graph shows a photocurrent response along the longitudinal axis of the device as a function of the quarter wave plate position. So the red arrow there indicates the longitudinal axis of the device. So the reason I bring that up is because the longitudinal axis is the crystal axis of the device. That's the way the crystals are oriented in the tantalum arsenide. And this is the direction in which you would expect a chiral current to appear. So this data we have here, note this, again, this is not an anomalous Hall voltage, but we think this photocurrent response that we have here is a combination of effects, including the coupling of circularly polarized light to chiral electrons in the tantalum arsenide. What's also compelling is this large linear response that we've got that appears in the transverse direction. So transverse is indicated by the arrow up there in the picture. So here the current peaks are actually due to the linear polarized light. Because in the transverse direction you don't expect to see a chiral current due to the chiral light. So everywhere where the light is chiral as a function of the quarter wave plate position, you see that the current is 0. And everywhere where the light is linearly polarized at the peaks, you have some sort of current response. And again, this is significant because there's no applied current present here. And we did see this response at room temperature as well. So, if you are still with me, it probably feels like I've been doing this to you guys. But I hope you will recall what we talked about, specifically a Weyl semimetal with an L called tantalum arsenide, whose low energy excitations are these chiral fermions, or chiral electrons. And we asked whether circularly polarized light can couple to those chiral electrons and produce this anomalous Hall effect. So our preliminary data hasn't revealed this effect to us yet at room temperature, and further testing is still required. But we have some very interesting effects in terms of chiral current that shows up. Again, we believe it's a combination of effects that are leading to this current response on the left here. And with that, I'd like to acknowledge a few people. Boston College and the NSF for funding this program. And I'd like to thank Dr. Birch and Dr. Lowry for organizing this whole program, but principally just for providing us with air conditioning. Gavin, thanks for working with me and always being generous with your time. I really appreciate that. Yitzi, thank you so much for helping us with all of our last-minute requests. That was super clutch. We could not have taken that data if Yitzi hadn't helped us out, so that was a pretty big deal. And Mason, thanks for always taking the time to help me get my thoughts in order. I appreciate that. And finally, thanks to Professor Nini at UCLA for actually growing the tantalum arsenide crystal, and Philip Moll at the Max Planck Institute in München for making the devices that we tested. And with that, I will take some questions.
So in the experimental mentioned the beam chopper. So
This guy.
What does that actually do? You said it like separates the beams.
Right. So the beam chopper, it chops up the beam at a particular frequency. So in the experiment we did, it's rotating at 531 hertz. Basically, because we want to see the response at that particular frequency. So we use a device called a lock-in amplifier that returns only the response data at that frequency and basically ignores everything else. So if you want to lock into one particular frequency, you need a beam chopper to create that input frequency, if you will. Does that make sense?
Yeah.
Okay.
So you said your sample had been destroyed a few times because of a increase in voltage.
Voltage spike, yeah.
What causes that?
It could be any number of things. One of the things that causes a voltage spike in our system are the preamps. So we have two preamps connected to the box, and literally when you press the power switch, it's one of those heavy ones that goes click, click, you know what I'm talking about? When you turn it off, it causes a voltage spike in the system. So if the sample isn't grounded when you shut off to the preamp or some other piece of equipment, you can get a voltage spike in the system.
So again, with your equipment, why is it that you're using a CO2 laser?
Oh, that's a good question. So the CO2 laser, essentially the reason you want to use a CO2 laser versus a more powerful laser is you want to minimize the amount of energy per photon so that you're only creating the excitations that you're looking for. Because if we use the more powerful laser, we would excite all kinds of other stuff, and we would also heat the sample up, and then you would get thermal voltage and all this other stuff. So we're using it so we can just focus down on the thing that we're interested in.
So your project has been to focus on tantalum arsenide as a Weyl semimetal to see if there's anomalous Hall effect. Have other Weyl semimetals been shown to have this effect? So is the question like, do they
other
do
Weyl-
it, or is like why focus on tantalum arsenide? Are there how many?
Yes, there are other materials in the class of Weyl semimetals. So like for one of the samples we were working with before our tantalum arsenide device arrived like middle of last month. Before that we were working with an niobium arsenide device, and there are other materials that you can also classify as Weyl semimetals that have these low energy excitations.
Is there any benefit of one versus another? Is it just ease of access and getting?
Well, we have the tantalum arsenides for one, yeah. That question I can't answer fully, yeah.
Don't look at me.
So I guess what is the point of figuring out the anomalous hollow belly? What is I don't know. I don't really understand the big picture of it.
Oh, because it's really cool and everyone wants to know about it. The primary interest is that the actual current response in the material is very fast. So the charge carrier mobility in the conductor is I think 2 or 3 orders of magnitude higher than like a traditional conductor. So when you apply the circularly polarized light, the current moves like much quicker than you would expect from something like copper, for example. So if you could somehow implement the material in like a high-speed sensor, the sensor could respond very quickly to changes in input. And also, just in use around other electronics, because it uses polarized light and not a magnetic field, it would play well with other electronics. You know? I don't know if you've ever put a credit card like next to a magnet. But
Yeah.
Okay, let's thank our speaker again.